Please do sign the sign-up sheet. It helps us track who's coming, and it also lets us send you announcements for upcoming presentations and speakers and other events that might be of interest. The seminar series is completely open. If you enjoyed it, please come back next month. And know that we have this every month, with the exception of August. We take a break over the summer. If you like these topics or you have suggestions for topics, please contact me. I'd love to hear about those ideas. And if you've got things that you'd like to present yourself, I'd love to talk with you about that for a future event. So today's speaker, we're really excited to have Dr. Don Hedecker here. He is professor of biostatistics in the Department of Public Health Sciences at the University of Chicago. And he is expert in multi-level modeling and different levels of clustered data and longitudinal data. We've asked him here because several of us across teams are collecting data that are clustered. And by clustered, what I mean is that you've got observations, say students within a school, or then schools within neighborhoods. Once you start thinking about clusters, you begin to see them everywhere. And if this is a new topic to you, it will change the way you think about data and the way that you approach your data. Dr. Hedecker was named as a Fellow of American Statistical Association in 2000. He has many leadership roles. We're delighted that he's taken time out of his very busy schedule to come work with us today and to give us this presentation. Our plan is to go until about 1 o'clock and then have maybe a little bit before then, and then leave some time for questions and discussion, and then we'll wrap up. I do want to give you a heads up that we record these, and so be mindful of your questions perhaps, or not. But we do that because not everybody can make it on a Wednesday afternoon, and we like to be able to share this experience with others. Hopefully we're moving towards technology of joining virtually, and maybe next year we'll have that capacity. But please, there are seats up front. There's a couple over here on the side too, if you'd like to come on in. Maybe some folks can squeeze in. But without further ado, delighted to present Dr. Don Hedecker.
Well, thanks very much. Thanks for inviting me here, Sue. Very happy to be here. And so for the next hour or so, while you're eating lunch, you'll also learn about multi-level analysis. And I'm going to try to make this pretty applied and understandable as best I can. So you might say, what are multi-level data? And this morning, I've learned that many of you do have such multi-level data. Typically, we think of these as data that are hierarchically structured, nested, or clustered. And so data are collected from units, organized or observed within units at a higher level. So you might have students within classroom. That's a classic case of multi-level data. Siblings within family, or repeated observations within individuals. And these are all examples of what are called two-level data. We have at level 1, students, for example. That's where you're going to measure your primary outcome variable and some other important mediating variables, perhaps. And then we have the clustering, say classrooms. And this provides the context or the organization of the level 1 units. And that might influence the outcome, and there might be some other variables here as well. So this is an example of two-level. What I'll get to ultimately is three-level sort of scenario as well. But two-level are pretty common in many areas. What's multi-level data analysis? Okay, so you got multi-level data. A lot of you seem to have multi-level data. What's multi-level data analysis? Lee Burstein had this quote way back when, 1985. I think it's still relevant today. Any set of analytical procedures that involve data gathered from individuals from the social structure in which they are embedded. So that part of the sentence is basically talking about the data, and are analyzed in a manner that models the multi-level structure. So that's the important aspect, is that structure is part of your statistical model. So not only do you have multi-level data, you actually recognize that structure of the multi-level data in the analysis. Okay? So it models the multi-level structure. And importantly, it recognizes the influence of the structure on the individual outcome. So the classroom could have an influence on the student grades. The family have influence on the sibling responses, health outcomes, for example. The individual has influence on their repeated observations. Now today I'm going to talk about clustered data in which we're going to have students nested within classrooms and schools. But of course, longitudinal data is another scenario where such models apply. Longitudinal is a little bit more complex in some ways because there's more correlation within subjects typically than within a classroom, let's say. And also there's a time ordering of the repeated outcomes that take into effect. But the class of models really are very similar. Okay. So why do you want to do multi-level data analysis? Probably main reason is to get a free lunch, right? Well, maybe you don't want to do it. You just want to hear about it to get a free lunch. Well, one reason that we might want to do is to find out about how much variability is there, for example, at the family level. How much variability is there at individual level? And we want to model the level 1 outcomes in terms of effects at both levels and potentially also interactions. So the individual outcome might be influenced by the family SES for males, not females, for example. Okay. Statistically, the reason that we do this is for this bullet point. Let's say we got 1,000 individuals that are nested within classrooms. If we do an ordinary regression, that analysis would assume all of these subjects are independent of each other. Okay. They're not independent. There's correlation of students within the same classroom. They're more similar to each other. That dependency needs to be taken into account into the statistical analysis to get the right inference. So the responses are not independent. There's some correlation that we want to address and account for. So I like to think of this as another example of what I think of as the golden rule of statistics. One person's error term is another person's career. I've certainly made it my career. Right? When I got into this in graduate school, I had no idea it would last this long, but it just continues forever and ever. Okay, so this is the golden rule, this golden rule of multi-level isn't quite yet on this slide, but we're working on it. We're working on it. Okay. Okay, so let's look at the data structure, and then we'll get into some modeling. So in a typical multi-level sort of data set, we'll have an ID variable that distinguishes the clusters. Okay, so here I got that going sequentially just from 1 to large N. Okay. Some of the software programs need the data to be sorted by that level 2 ID variable. Not all, but some do. Okay. And now within each cluster, we have a number of rows for the individuals observed within that clusters. Now, I know most people don't like notation, but I'm here to explain to you, notation is your friend, right? It's your friend. It's going to tell you something interesting in compact matter. So little n indicates the number of subjects in a cluster, but notice it has a subscript. What that subscript tells us is that the number of subjects per cluster can be different. Okay, so the number of subjects in classroom 1 are different than classroom 2, 3, et cetera, et cetera. That's important because in real data, it's typically the case that numbers of subjects within clusters is going to be different. It's not going to be the same. If it's the same, there's two possibilities. It's textbook data or it's simulated data, right? Real data, it's never the same typically. Okay? So we have different numbers of rows per cluster, and then we've got some variables that are measured at the cluster level. It might be what's called a cluster randomized trial in which clusters are randomized to treatment group. Okay, that would be a variable that then is the same for all elements, all subjects within a cluster, right? Maybe the size of the cluster is a variable that we have that we want to use in our model. Okay, so we'll have a series of cluster level variables in our data set. Now, most of the software wants the data set up like this and doesn't care that there's redundancy here. In other words, this value is the same as this is this. HLM is a notable exception. They allow you to read in a level 2 data set and a level 1 data set, and then they bring them together. Most other software packages just operate on one data set like this. Okay? And admittedly, there's some redundancy then, but it's not really important per se. And then at the subject level, we have, of course, a dependent variable, the outcome. And then we might have some subject level variables like their sex, their age, things like that. Okay? So the data structure is in this long manner. Each subject occupies a row, and we need to know which cluster does each subject belong to, right? So if we don't have this variable here, we can't really do a multi-level analysis per se. If we don't know which subjects belong to what cluster, we need to know that information. Okay? And here's longitudinal. It's the same basic skeleton for the data set. Here we have, as the clustering variable, the subject ID. And then within each subject, we have the repeated observations nested within. And again, an important facet here is that the number of repeated observations can be different from subject to subject. And that's really how I got interested in these models when I was in graduate school, because I was doing a lot of work on repeated measures analysis. And the traditional methods back then in the Stone Age required people to have the same number of observations. Right? And most studies that I analyzed, that wasn't the case. People were missing at some time points, they dropped out of the study, et cetera, et cetera. So the multi-level or mixed model was developed largely with that in mind, to allow for different numbers of observations per subject. Okay? And there we might have some variables that are at the individual level, time invariant covariates. In other words, they don't change values across time. Maybe it's a subject randomized study, so treatment groups at the subject level, their sex, their age. Of course, age does change across time, but unless you're Dorian Gray. But for most of us, it changes the same, so we have like age at baseline, something like that. And then we have time-varying outcome, and then maybe a dose variable or something like that. And what we're interested in longitudinal oftentimes is modeling the change across time, and is that related to treatment group, for example, something like that. So notice the data structure is the same for clustered as longitudinal. Again, in longitudinal, there's a bit more issues because the data are more correlated. The variance could change across time. The correlation could be different across time. But the basic structure and the basic class of models really the same. Okay. So today I'm going to call these multi-level models. Tomorrow I might call them random effect models. In different literatures, you see these models called somewhat differently. In the social sciences, it's common to call them multi-level models or hierarchical linear models, HLMs. Right? In the statistical literature, it's a little bit more common to see them called mixed models, mixed effects models. In econometrics, they often call them random effect models. They're truly mixed models because they have fixed parameters and random parameters, but the random effects are kind of the stars of the model. So when they say random effects models, they're just pointing out that those are the distinguishing parameters of the model. They're useful for identifying or for analyzing cluster data. And so here's various kinds of clusterings we might have: clinics, hospitals, families, work sites, schools, and longitudinal data. Now, what I'm going to talk about today is where we have strict hierarchy. We're going to have subjects within classrooms and schools. But as I was mentioning with some people this morning, sometimes there could be cross-classified random effect. So a kid could be nested within a neighborhood and a school, but not all kids in the same neighborhood go to the same schools. Okay, so there could be these two clusterings, but they're not hierarchical, they're crossed. And those are just cross-classified multi-level models then. Okay. Okay, I know you've been saying since noon, show me the equations, enough of these words. So here, right, everybody wants to see the equations, right? Okay, so here's the equations. The first thing I want to emphasize is what I'm talking about today is essentially just a regression model. It's an augmented regression model, but it's a regression model. So what that means is that everything that you learn about simple and multiple linear regression applies here as well. We're going to have a predictor, a dependent variable y. Here, I got it written as a vector for the vector of responses from a given cluster. So that's just the outcome variable saved from all kids in a classroom. Okay. I'm going to have predictor variables in x. Okay, so what does x contain? X contains everything that we use in ordinary regression. It could have continuous variables like age. It could have indicator dummy variables. It could have polynomials. It could have product terms. Everything that you learn about multiple regression applies here, because this is just a multiple regression model with one augmentation. The augmentation is that here I have a cluster effect. Okay? Here I'm using the Greek letter epsilon I to represent the effect of the cluster on the subject. Okay, so I here is for the cluster, and these effects in a mixed model are said to be random effects. What does that mean? So you might think of this. I've got 30 classrooms. Why can't I just put in 29 dummy codes to represent the differences between the classrooms? You can. That would be a fixed effects approach for dealing with the clustering. But that kind of modeling would say that the inference is only about those 30 classrooms. That's your population. Okay? In this way of dealing, what we're saying is that the classrooms we have are representative of a population of classrooms that we want to make inference about. Okay? That's why we're characterizing this as random effects. They come from some population. In statistics, if you have a random variable, it means there's a distribution. Okay, so you're on Jeopardy. It's like what the normal distribution is up there. Your answer is what is the most common distribution dealt with in statistics, right? So it's normally, and the clusters are independent of each other with mean 0 and variance sigma epsilon. Okay? So this line right here is what distinguishes this from an ordinary multiple regression model. And this is what takes into account the fact that clusters have influence on the students in that particular classroom. Okay? Now, let's say there's no clustering effect. What's going to happen? All of these cluster effects will go to 0. The cluster variance will go to 0. Okay? So the cluster variance is the indication of how different are clusters from each other. If there's a big clustering effect, that variance gets large. There's a lot of heterogeneity attributable to clusters. If there's not much clustering effect, that variance gets small. All clusters are very similar to each other. Okay. So that parameter is an interesting one. It tells us the degree of clustering in our data set. And then finally, since it is a statistical model, we have an error term. That's the residuals that also have a variance attached to it, the error variance. Okay. Okay, so ordinary multiple regression with one notable augmentation, allowing the cluster to influence the observations in the cluster. That's the epsilon i's. Is that right? I guess so. See, oh, here it goes. I thought I was jumping over one. So as the cluster subscript I is there for y and x, it just means that the sample size can be different from cluster to cluster. Okay? X is going to include usually what we have in X. Covariance measured at cluster level, subject level, interactions. Again, it could have continuous variables like age, categorical dummy variables, product terms, polynomials. Just the usual suspects in X. Okay. Number of covariance we might designate with P, and we typically have an intercept in our model, so the number of columns in X is P plus 1. Okay. So the distinguishing feature really is this random effect epsilon I. Okay? And this is what distinguishes this from an ordinary multiple regression model. Okay? It represents the effect of clustering. As I mentioned, if there's little clustering effect, these epsilons will be close to 0, and the cluster variance will approach 0. Okay? If there's a strong effect, they will spread out, and this will increase from 0. Okay? So the cluster variance is what's interesting here to tell us how much clustering goes on. Okay? So in a statistical journal like JASA, you might just see the model written as that top line. Y is distributed normally with mean x beta. Okay, so x beta is the usual mean from a multiple regression model. Okay? Y has mean x beta. And the variance covariance structure there has that compound symmetry structure. Within a cluster, the variance has two components, the error variance and the cluster variance. And the covariance of any two subjects within a cluster have a covariance element of the cluster variance. So again, this is what's sometimes called the compound symmetry structure. What this gets to is a way of designating the strength of the clustering effect. Okay? So in ordinary regression, you want to tell people how good is your model. What do you typically use as the one statistic to tell people how good is your regression model? Anybody want to guess? R-squared. Oh, God, you guys are, wow. Usually when I teach this, I get all kinds of different answers. But R-squared is the right one. Right. And R-squared lives between 0 and 1, right? No matter what the scale of Y is, scale of X is between 0 and 1. The ICC that I have written here, the Intraclass Correlation, is like R-squared. It takes in the numerator the cluster variance, and in the denominator the error variance plus the cluster variance. So there's no cluster effect. The ICC goes to 0. If there's total clustering effect, it goes to 1. Well, I'll tell you, it never really gets towards 1. With longitudinal data that are close in time, it can get pretty darn high. Okay? In the scenarios that I'm going to talk about today, it's typically more on towards the 0 side, but not negligible. Okay? But the ICC is a way of describing the strength of the clustering effect. And it's something that's often reported when you're dealing with multi-level models, is how big is your ICC? And many of the software programs these days calculate for you automatically, give you a confidence interval, something like this. Now, it's called intraclass correlation, but of course in educational research, class means classroom typically. So Harvey Goldstein suggested that it might be better to call it intra-unit correlation, like intra-family correlation, intra-clinic correlation, something of that. Sensible idea. Nonetheless, you often see it called intraclass correlation. Okay? It has this takes on values between 0 and 1, tells you how similar are the measurements within a cluster. Okay? It's the ratio of the variability attributable cluster over the total variability. But it's really the unexplained variability. Now, this is a kind of subtle point, but realize it's the variability of y given x. Right? You've got x in the model. It's the residual association. What that means is that the ICC can be different depending on how many covariates you have in your model. And what sometimes people do in multi-level models is they'll estimate what's called a null model. One with no x variables, figure out what the ICC is, and then see how it changes as you're adding in important predictor variables in x. Now, in general, it tends to be larger for smaller clusters. This was known in the sampling literature by Kish a long time ago and Alan Donner a little bit more recently. And they just gave these kinds of rules of thumb. For spousal pairs, you often see ICCs between 5 and 12%. For physician practices, it's smaller, and for counties, it's even smaller. But realize, even small ICCs can mean a lot because you're talking about a lot of individuals in those particular clusters. And another thing it can change is depending on the dependent variable. Now, that really came into my mind. I was working on a study in psychiatry a long time ago. Regina Kasper was the PI there. Rather small study. There were 26 families and 63 sisters. The interesting thing about this was one of the sisters was suffering from anorexia. Okay, so it was one sister suffering from anorexia, and then 1 or 2 or 3 of her sisters. Okay. So I calculated null models there, first looking at height, for example. Okay, so this is height in inches, I assume. 64 is the average, right? 5'4". Okay. Estimated the family variance, the residual variance, got an ICC of about 1/2. Right? Okay. So there's a strong association of sisters within the same family. That's a high ICC, right? As one would expect. There's a large genetic component to height. Okay, now I'm going to confess that I'm the dumb statistician. For me, it's just X and Y. Because in the middle slide, I have psychological factor. And probably those of you who might be in psychology will say, well, what is it? Is it stress? Is it anxiety? What is it? I don't remember. I just put psychological factor, right? Pretty stupid, right? Anyway, I estimated this model for these data. I got an ICC of about 1/3. So whatever it was I was measuring, presumably it was unrelated to anorexia, to that disease, because it's a pretty high ICC. So individuals within the same family are pretty highly correlated on this particular psychological factor that I didn't write down what it was. Now the last one is interesting, BMI. Now in most studies, BMI would be highly correlated within families, just like height, right? In this, it goes to 0. Right? Why? One of the members of the family was abnormally low on weight, right, because of their disease status, right? So it kind of reminded me, yeah, the ICC can change depending on the dependent variable, but also the study type. In most studies, the ICC for BMI would look like the ICC for height, right? In this particular study, in which one of the members of the family had a very aberrantly low value of weight because of their disease, there was no association. Okay, so I just point this out, that realize you sometimes see these rules of thumb about ICC. You know, they are rules of thumb. Right? They can definitely change. Okay, so here's an example that I worked on a long time ago published in Journal of Consulting and Clinical Psychology. This data set is a very good one for illustrating some of the advantages of multi-level modeling. So it was a smoking prevention and cessation project conducted by Brian Flay. When he did this, he was at University of Southern California. When I worked with him, he was at University of Illinois, Chicago. And then after that, he's moved on to the West Coast. He's in Oregon somewhere. But at that time, he had this data set that had 1,600 7th graders nested within 135 classrooms, nested within 28 schools from Los Angeles. And so when I first did this, I said, 1,600, really? How many times do you get a round number like that? That's what it was. Sometimes it happens. It was highly unbalanced. And I don't know precisely why it was so highly unbalanced, but there were between 1 to 13 classrooms per school in this study, and between 2 to 28 students per classroom. Okay. The outcome that we were interested in here was their knowledge of the bad effects of smoking. Okay. So it was a knowledge of the effects of tobacco use, and the timing of the study is such that students were tested at a pretest time point, and then I think it was about 3 months later, they were again retested. Now, in this particular study, it was a cluster randomized trial, or what's sometimes called group randomized trial, in that schools were the unit of randomization. Okay, so why in this world would you not randomize at the student level? There'd be issues of contamination. Kids talk to each other, right? So in school-based research, it's common that the randomization is going to occur either at the classroom or the school level because of worry about contamination. Okay. That might be less true if the study is, conducted on the internet or something like this, but still, there's many scenarios in which you can't really randomize at the subject level because of issues of contamination. This was one of them. Okay. So schools were randomized to basically a 2-by-2 crossing of 2 factors. The first factor was a social resistant classroom curriculum. Okay, so again, substantive people will say, what was that? And here's my interpretation of that. A health educator came into the classroom and educated these kids about the dangers of tobacco use, right? And in a socially resistant kind of way, whatever that means. Okay, so some kids got that, the classroom curriculum. Some kids got a television intervention. What was that? My understanding of that was an AV person came in, plugged in a TV, and said, hey, kids, watch this health educator talk about the dangers of tobacco use. Actually, it was something more than that, but it seems more funny having an AV person coming in with a television, right? And of course, if that's effective, that could be useful because that costs less to implement than having an educator actually come in and talk to the kids. Okay. Then there was one group of schools that got both, and then finally a group that got neither this classroom curriculum or the TV. So it's a 2-by-2 crossing of television and the classroom curriculum. Now here shows the descriptive statistics of this tobacco and health knowledge scale at pre-test and post-test. Going across are the 4 treatment arms. Now let me tell you a little bit about the dependent variable. What it is just 7 questions about the bad effects of tobacco use. And what we recorded was simply the number of questions that they got correct. Okay? 7 questions. At baseline, how many are they getting correct? 2. They could have flipped the coin, probably did better than what they did on average, right? So they have a lot of room for improvement here, right? At baseline, they're scoring all about an average of 2. And on top, I have the numbers of kids in these different arms. Now, realize, this is a group randomized study. So there's no guarantee that the students will be the same, necessarily, at baseline. Schools were randomized, students were not. What we see in terms of the pretest, they're all very similar in their mean on this particular variable. Okay. Now, 3 months later, the kids that didn't get anything, they improved by about 1/5 of a point on average. Okay. So, you always see this with test, retest. If you saw the test before, you're likely to do better the second time you see it, regardless of anything else. Okay, so you see a little bit of that. Then the kids who got television but not classroom curriculum, they improved by about 1/2 a point. Okay. The kids that got the classroom curriculum but not TV, they improved by nearly a point. And then the kids who got both, the combo version, you guys have in Chicago a very popular thing to order is a combo. Anybody, you know what I'm talking about? You go to your hot dog stands and you ask for the combo. It's the Italian sausage with the beef, right? It's greatest thing, right? I've heard that. I know some friends of mine who moved to San Francisco. They don't have them out there, so it's like. So if anybody really wants to make money, go to California, open up a hot dog stand with the combo. So the kids that got the combo, interestingly, they didn't do the best actually on average, right? So as we're going to see, there's some suggestion of interaction here in that the television seems to be beneficial here, but not here. Okay, so that's the eyeball statistical test that we're going to now pursue a little bit more rigorously. Okay, so here I got to write up the first model as a multi-level model. Let me tell you my first experience of multi-level modeling. I finished my degree. I was working at UIC, University of Illinois, Chicago, and the Department of Sociology chair calls me up on the phone. Back then we had phones. Remember those? Not cell phones, actual desk phones. Right? I pick up the desk phone. He says, could you come over and teach a class for our graduate students on multi-level analysis? I was like, oh, I'd love to do that. There's just one small problem. I don't know anything about multi-level data analysis. He said to me, well, I thought you did a dissertation on mixed models. I said, yeah, I did one on mixed linear models. He goes, it's the same thing. Oh, so that was my first, aha moment. Multi-level models and mixed linear models, it's the same thing. So I then, at that time, there were basically a few sources on it. There was a book by Harvey Goldstein and a book by Brighton Roundbush, HLM. And as soon as I opened these books, I'd see these multiple equations. And I was like, what's going on here? There's one equation, there's one model, right? I wrote it before, y equals x beta plus epsilon plus error. There's one equation. What's with these within, between, blah, blah, blah? Well, if you've taught a class, you know that when you teach something, you have to at least pretend like you like it, right? You have to at least have that sort of presentation. So I struggled through this teaching course of 15 weeks, writing it up as multi-level HLM sort of way, pretending that I like it. Guess what? By the end of 15 weeks, I did like it, in fact, because it helped me to understand the model and the interpretation of the model much more clearly than when I just wrote it as the one equation. So the software doesn't require you to write it up as a multi-level or HLM, but still to this day, oftentimes when I'm doing some modeling, I write it up that way because it helps me to understand precisely the meaning of the variables. Okay, so now what I'm going to describe is this. At level 1, we have the outcome, the post-test tobacco health knowledge scale. That's my dependent variable. That's my outcome variable measured on student J within cluster I. Okay? And in terms of covariance, I'm going to put in the level 1 model any covariate that's measured at the subject level. Okay? So I'm going to bring in pretest. The reason I have in brackets, what I want to show you is what happens to some of the parameter estimates when I bring in this variable versus I don't have it in. Okay? So pretest is going to be brought into the model on the next slide. Now the first thing, epiphany, is that these coefficients, the intercept, the slope for pretest, they come down at level 2 to be modeled in terms of any cluster level variables. Okay. So I'm going to put in as a cluster level variables the indicator of whether they got classroom curriculum or not. Now notice it only has an I, because it wasn't varying for individuals, it was varying for clusters. It's a cluster level variable. So it's at level 2. Okay? Okay, so here what I'm saying is that the classroom intercept, let's say we got students within classrooms, depends on whether they got classroom curriculum or not, plus a random component that's not explained by classroom curriculum. A level 2 residual, this is sometimes called. That's the effect of the classroom on the outcome. Okay. Notice for B1I, the slope for pretest, I just say that's equal to beta 1. Okay, so what I'm saying there is that there's one effect of pretest on posttest. That's it. Let's say I wanted to build into this model the possibility that the effect of pretest varies depending on whether they receive classroom curriculum or not. What would I do? I would have a similar specification like this down here. Okay? And that would be an interaction of classroom curriculum by pretest. Okay. Here's another idea that this multi-level way of writing it points out. I have a random component here. Could I have one here? The answer is yes. Okay, that's easy. Yes. What does it mean? That's harder. Right? What it would say is that the relationship of pretest to posttest varies from cluster to cluster. There's heterogeneity in the effect of pretest on posttest. Is that possible? Sure. Right? So that might be something that you would be interested in examining. If I just write it out as a one equation, I don't think that idea would necessarily ever hit me. When I write it up in this multi-level way, I come to realize any variable at level 1, any covariate, its effect could be random at level 2. There could be additional heterogeneity in the effect of clustering in this particular way. Okay. So here, again, what I want to point out is what happens in particular to the variances, the level 1 or error variance and the cluster variance, as I bring in pretest and post-test. Pretest and classroom curriculum. Okay, so I did this two-level analysis two ways. One, students in classrooms. Second, students in schools. I'm going to get to the three-level in a moment. Here, the first column has the students in classrooms, the null model. So the model with no covariates. It has an ICC of approximately 10%. The analogous model of students within schools has the ICC of about 7%. Okay? So students within the same classroom are more similar to each other than students within the same school. Okay? There's clustering at both, but it's stronger at the classroom level, as you might expect. Okay? Now, I bring in pretest score. It has a positive coefficient in both models. Incidentally, what this has is the estimate and then parentheses the standard error. So a wall test would be the ratio of that. And if that ratio exceeds 2 approximately, it would be a significant result. So pretest is certainly related to post-test. And if they scored higher on pretest by 1 point, they score higher on post-test by about 1/3 of a point. Okay? So that's the effect of pretest on post-test. Notice what happens to the variance components. They both diminish. Okay? So adding in a level 1 variable can explain some of the error variance. It's now being explained. Also, the level 2 variance. And so the ICC now goes down to 9% in this case, or in the students in school, it goes down to 6%. Okay, now notice what happens when I bring in classroom curriculum, which is not at the student level, it's at the cluster level. It's got a positive effect in both models, highly significant. Kids that got the classroom curriculum do better by about 1/2 of a point on average than kids who didn't. The cluster variance has been diminished. The error variance is the same. Okay, so when I first did this, why is that? Well, if you look at the multi-level way of writing it, you get a glimpse of that. Adding this in diminishes the variance associated with this. It's just like ordinary regression. You bring in a predictor variable, the residual variance diminishes. Adding in this variable diminishes the level 2 residual variance, the cluster variance. Adding this in does nothing to the level 1 variance because this is not at the subject level. It's at the cluster level. Okay? So what I've done here with this slide here is explain some of the reasons that classrooms and or schools are different from each other by knowing whether they got the curriculum or not. Okay? On the very bottom, I have the log likelihood value from these models. These are nested models, so I could do likelihood ratio tests comparing, for example, this model to this model, or let's see, this model to this model, I believe it is. And so those are significant improvements in model fit. But that's the important thing I want to make is that when you add in a level 1 covariate, it can diminish both level 1 and level 2 variances. You add in a level 2 covariate, it diminishes potentially level 2 variance, not level 1. Now here's another thing. In the old days when I first worked on this paper, when multi-level models weren't so common, what people did with data set like this is, what was advocated is this approach. Well, do an analysis in which you ignore the clustering. So just an ordinary regression model, forgetting about the clustering of the data. Okay, that's an individual level analysis, let's say. And then secondarily, let's do a cluster analysis in which we say aggregate to the classroom level. We get the classroom means, and we treat that as the outcome, and we use the classroom covariance as the predictor variables. So one's an individual level analysis, ignoring the clustering. The other one's an aggregate analysis. Really, the multi-level model has both of those cases as special cases. Okay? Because here, I've got that idea. I'm taking the post-test, and here I'm not including pretest, so my B0I really is the mean of the cluster, let's say of the classroom. And level 2 there, I'm regressing the mean of the cluster on those components of the design, classroom curriculum, television, and product term. Okay. So if the cluster effect is completely explained by condition, then these cluster effects will be 0, and this would be the same as the individual level analysis. Right? It'll give you exactly the same results. And if the cluster sizes were all the same, and in this case there's no level 1 covariance, then this model would give the same as that aggregate analysis. Okay. Now typically neither of these two if statements are ever met. So this multi-level model really has these two old-fashioned ways of doing things as special cases, but the special cases are really rather unlikely, because it's rather unlikely that the random effects will all be 0 for all cluster, and it's, again, unlikely that the sample size would be the same, and that you don't want to have any level 1 covariance. Okay. But I just point out this connection to those more traditional methods. And here I show this in this particular case where I have an ordinary regression analysis here at the class level, 135 classrooms. I have a student level analysis ignoring the clustering. Okay. What would I determine in terms of significance? I would say, well, there's a strong classroom curriculum effect from both. However, the student level analysis would say that there's a significant interaction. Okay. Classroom analysis, it's virtually 0. Okay, so the old way of doing things, you'd be shaking your head. What do you conclude? Is there interaction present or not? This analysis says there is. This analysis says there's not. Okay. Multi-level comes to the rescue, right? It tells us basically that there is a significant classroom curriculum effect, but the interaction is not quite statistically significant. Okay. Now notice this from this slide. The residual variance in this classroom level analysis, 1.86. That's the sum of these two. Okay. Right? Because basically, again, what this analysis is saying is that it's all noise. The multi-level analysis is saying, hold on a minute. It's not all noise. There's a component that's attributable to the classroom. Okay. So it separates this out in terms of what is noise and what has some systematic component. Notice also the standard errors there in the student level analysis compared to the multi-level analysis. What do you see? The standard errors from the ordinary analysis are all smaller. Why is that? That student level analysis acted like there were 1,600 pieces of independent information. The multi-level analysis says there's 1,600 pieces of information that are correlated to some degree. Okay. What drives standard errors? Sample size. More sample, smaller standard errors. So this model is acting like it's got 1,600 pieces of information that are independent. The standard errors are quite small relative to this. That says, wait a minute, we don't have quite that kind of sample size. Right? 1,600 pieces of correlated information, correlated to some degree. Really, that's why multi-level is useful. Another reason is here you're likely to get type 1 errors, calling things significant that are not truly significant. Okay, so finally we'll get to the analysis that we published in the paper where we had both pre-test and classroom curriculum, TV, and the product term. And again, this is when we did the paper. I don't think I had yet written it up as multi-level model, so I didn't even think about the possibility that pretest could have a random component. Okay. But certainly writing up in a multi-level way informs us that, yeah, that's possible. I know this is rather small to read, but let me just walk you through it. On the left-hand side of the bar, I have the aggregated class-level analysis, and then I had the student-level analysis that ignored the correlation of the data, and then here I had students in classrooms, students in schools, and then finally the 3-level analysis, students within classrooms and schools. And what I'm designating as highly significant results are ones with, say, 3 asterisks, 2 indicate 0.05, and 1 indicate marginally significant. Okay, so sometimes people call that approaching significance. I once heard a statistician, who I can't remember who said this, but I thought it was pretty funny, said, well, maybe it's not approaching significance, maybe it's running away from significance. You know, you get 0.06, 0.07, you're always thinking, well, it's going in the right direction. Maybe it's actually going in the other direction. Okay. This is why this data set is kind of useful for showing multi-level, because the ordinary class analysis would say only pretest is significant and classroom curriculum. No effect of TV, no interaction. The ordinary analysis at the student level that ignores the clustering of the data would say everything is significant at 0.05 level. Okay. So Pretest is significant, classroom curriculum is significant. There's a positive effect of TV, there's a negative interaction. Everything is significant. Okay, so again, in the old way of doing things, it's like you wouldn't know what to determine about the television effect or the interaction. Because the aggregator analysis says those are not significant. The individual says they are. This also points to something. Notice the pretest and classroom curriculum, they're significant across everything. Right? If you have strong data, you don't need me. Right? If you have very strong data, you can do the stupidest thing and get the right result. Right? But it's for more of the subtle things where it's important to do the right modeling choice. Now, all of the multi-level analyses, at best, they find a marginally significant interaction students in schools. Okay? So they agree on the fact that there's a significant pretest and classroom curriculum effect, but thereafter there's no TV effect, there's no significant interaction. Now, you might ask, which of these three models would you want to publish on? Okay. When we did this paper in, whenever it was, back in the Stone Age, there was software out available for 2-level analysis, not so much for 3-level. So what we pointed out in that case is that if you had to choose a 2-level analysis, probably students in classrooms would be the one, because the classroom variability is considerably larger than the school variability. However, since that time, it's quite easy to estimate 2 and 3-level models. So I would advocate that the 3-level analysis is the proper one for these reasons. Regardless of statistical significance, the unit of randomization was the school. Schools were the unit of randomization, so therefore schools should be in the analysis. The curriculum was delivered in the classroom. So classroom is also a component of the design of the study. So to me, it seems that the 3-level analysis makes the most sense. And again, what you see with the variance is that the error variance here of 1.69 is partitioned in these multi-level models in this way. And also that the standard errors from the student level analysis, which ignores the correlation, considerably smaller than the models that take into account this clustering of the data. So the results, the conclusions vary about the interaction in particular differ. The student level results are pretty close to multi-level, but the estimates are more similar than their standard errors. And this underestimation of the standard errors is expected, since the student level analysis would ignore the fact that the observations are not independent. The students are a bit more homogeneous in classrooms than schools, and the 3-level model is rather close to the students within classroom model. And based on that 3-level analysis, about 4% of the variation is at the classroom level and about 1.5% at the school level. So here I can compute some ICCs. Here I have 3 actually. I can calculate what's the similarity of students within the same school. That takes in the numerator the school variance, and in the denominator the error variance, the classroom and the school variance. That gives me this estimate of 1.5. Students within the same classroom, here I have in the numerator the classroom variance and the school variance, and I got an estimate of about 5%. And then one could also express how similar are the classrooms within the same school in a way that's kind of like taking the classroom averages and saying how similar are those clustered by school, and there I get an estimate of about 0.3. Again, this represents the fact that there's more variation at the classroom level than at the school level. Now, one thing you might want to also do is to get R-squared kind of measures. Joop Hoeks, who's got a very good book on multi-level analysis in 2nd edition, suggested this. What you do is you estimate a model with no covariance. That's the Null model. You get an estimate of your error variance. You get an estimate of your cluster variance. You then re-estimate the model with your covariance, and that's what's in the numerator of those formulas. So subscript O or 0 refers to a model with no covariance, P with P covariance added. You then do these calculations, and we can see that from the students in the classroom model, I'm explaining about 7% of the variance. Classroom, we're explaining about 55% of the variation at the classroom level. So sorry, this is 7% of the variation at the student level is what I'm explaining, and about 50% of the variation at the classroom level is being explained by this model. And you can do the same thing for 3-level models to see that, again, we're explaining about 7% of the variation at the student level, about 25% of the variation at the classroom level, and about 76% of the variation at the school level, okay? By using these covariates that I have, just these 4 or 5 covariates. We can do likelihood ratio tests. Let me just go over this. We're kind of getting towards the end, so I'll just go through this. This is just comparing some of these models, the student level model, the students in classroom, students in schools, and then the 3-level model. And they're all significant. Let me just say a little bit about 2A. Here what I'm doing is comparing the 3-level model to the student in classroom model. Okay, so here on this last row, I'm comparing the 3-level model that has a school variance to a 2-level model that has classroom but not school variance to answer the question, if I account for the clustering by classrooms, do I additionally need the clustering by schools? I get a nominal p-value of 0.053, but realize this is what's called the half p-value. And why is it half? Because the alternative hypothesis, null hypothesis is the variance equals 0. The alternative hypothesis is that it's greater than 0. So we want a one-sided test. Okay, so that's what that's all about. And if you're interested in this testing, Snyder's and Bosker also have a very good book. Actually, this is from the first edition. They have a second edition as well. Okay, so I skipped over this slide. Pardon me, but you're the geekiest bunch of pirates I've ever seen. We're software pirates. Right. So what software can you use to run these models? There's lots out there. Spss, SPSS, Stata, the dominant packages are. They all have facilities to do this. Here I just listed some references that there are for these different programs. In SAS, it's proc mixed. That's largely used to fit these models, and there's a good article by Singer and some other materials. SPSS, there's a paperback book that's recently been published by Heck et al. That has some bits in there. Stata, Ray, Hesketh, and Schrondel have a very good book as well to run these. Let me just show a little bit about the software. Also, I worked on a program called Supermix. Let me do my little bit of commercial. It's free in a student version, and a student version can run many of these kinds of models. What Supermix has within it is the capability of modeling continuous outcomes, dichotomous outcomes, ordinal outcomes, nominal outcomes, counts. So all of those different kinds of dependent variables. Here shows some SAS code to run it. Again, it's run using proc mixed, and above it here I have a proc regression specification. So the primary difference here is just indicating here, oh sorry, this is proc mixed without paying attention to the clustering. Then when I pay attention to the clustering, I have a random statement. Okay, so that's the only thing that's necessary to really account for the clustering here. I show on the top is clustering by class, clustering by school, and then for 3-level analysis, I have clustering by school and clustering by classroom within school. Okay, so it's quite easy to run 2 and 3-level in SAS. Likewise, in SPSS, I know some of you use SPSS, they have a mixed procedure that, and looking it over, it looks very similar to SAS proc mixed with a little bit of difference, but not much. You also have a random statement. Here for a 2-level analysis, for example, you have 1 random statement. For a 3, there would be 2. They indicate the nesting of classrooms within schools in this slightly different way than SAS, but it's quite similar. Let me say a few things about the options I specified. And if you're interested in getting the code in the data set, there's a web location that you can get these materials. I generally use maximum likelihood as the default estimation. By default, the programs often use REMO estimation. What's the difference? Ordinary maximum likelihood gives you variance estimates that are slightly too small. REMO corrects for that. But the difference is this. If I want to do a likelihood ratio test comparing nested models that have different covariates, I can't do that under REMO. Because REMO adjusts for a number of covariates in my model, whereas maximum likelihood doesn't in getting the likelihood value. So I like to do likelihood ratio testing of comparison of models, so I typically use maximum likelihood as my default. And this little bit of bias in the variance estimate, it's really not an issue when you have sample sizes like this, with 1,600 subjects. The other thing is, by default, SAS and SPSS won't print out wall tests for covariance parameters. The reason they they don't print those out is they do have dubious statistical properties. However, I usually ask for those, and you might say, why do you ask for those? Because I want to get arrested by the statistical police. No, this is the reason. If you don't ask for code tests on either SAS or SPSS, you won't get this estimate of the standard error of the variance parameters. Now, standard errors are usually telling when your model is not properly converged or not. Right? It's not often the point estimates themselves that look weird. Standard errors look weird. They're either like really small or really big. Okay, so I want to know that as a diagnostic to see the standard errors of every single parameter I've estimated in my model to see if they're strange. So that's the reason I select that option. This just has some of the output that both in SAS and SPSS. Let me just summarize here. So really, these are just augmentations of simple multiple linear regression models, including cluster effects, random cluster effects. Today I talked about continuous outcomes, but these models have been developed for all kinds of outcomes: dichotomous, ordinal, nominal counts, time to event. These are all members of what you might consider generalized linear mixed models. And again, in the statistical or biostatistical literature, you'll see what I talked about today, often referred to as linear mixed model. And then the second bullet point would encompass generalized linear mixed models. I mentioned to some people today that you might have cross-classified multi-membership or dynamic group structures. So again, cross-classified when it's students in the neighborhood and high school, but they don't all go to the same high school. So I worked on a paper with Guy Caffrey and Psych Methods that we published on this, and that also has some code in different software packages to run these other kinds of multi-level models. And again, you can use many software programs these days to run these kinds of models. And for continuous normal outcomes, they basically do the same thing. They give slightly different options in terms of how to do things, but they're generally the same. There's more differences for non-normal outcomes, where estimation is a bit more complex. I tend to favor full maximum likelihood estimation using what's called Gaussian quadrature. That's what you'll find in Stata and SAS glibmix and supermix. I'm not so sure about the others. Some of them do what's called quasi-likelihood that I don't tend to prefer. And I think that's the end of the talk, so it looks like it's almost 1 o'clock. Do we have this room till 1? Or past that?
Past.
Oh, darn, because I always try to have my talk end when we got to leave so I don't have to answer any questions. No, I have to answer any questions you might have. Yes?
Could we get a copy of your slides to keep thinking?
Yeah, I believe so. Sue, is it possible for people to get this I mean, you can send me an email.
We can make sure, if you're okay with that.
Yeah, sure.
We can make them available.
Yeah.
And the video will be up on the website as well.
Yes.
You probably don't want to watch that though. But unless you're having trouble sleeping, then put it on. Yes, question.
So in most of the multi-level models that I've run, I typically do a good job of explaining for level 2 variability. Is that typically what you find, that you do better at level 2, but not as good at
Sure. I mean, if you think about it here, at the student level, all I have as a predictor is pretest, and then what they got basically. There's a lot more than that explains why a kid knows about tobacco use, right? So yeah, what you're saying is exactly right. That's often what you find. So I could have a richer model at the student level, but really, this is sort of like the outcome model for this particular study. I think I have the pretest in because that's certainly related to post-test, and then I just got the design variables in, the intervention components. Yes.
So can you talk a little bit about what we talked this morning about? Is that I'm curious about whether or not the cluster itself have characteristics that would explain this.
Right.
And that might be incredibly informative to intervention studies.
Right.
So
Right.
is that a proxy for something going on at that?
Right. I mean, even think about this. I showed, going back to this slide, with the ICCs. Yeah, here. So, say for the 3-level model.
Epsilon.
Yeah. This is the variance at the classroom level without any covariance. And then this is what it changed to when I added in, for example, did they get the classroom curriculum? Did they get the TV? And then the product term. So just knowing those things changed it by this amount. Likewise for the school. School went down quite a lot, actually. Right? So that's an example of what you're describing, but certainly one could be much richer with the covariates than trying to explain. Right? And this model, you're saying that schools are pretty different from each other. In this model, saying, wait, not so much. Why? Because I know whether they got what they got. And there could be additional things that you want to look at.
I was thinking actually within it, like, so what if the classroom, what if the curriculum characteristics, so maybe it was the type of teacher.
Sure.
Or, like, if I think of patients within practices, is it something about the practice itself
Right.
that actually causes the cluster effect?
Yeah, sure.
So how do you then, so now you're collecting cluster characteristics.
Yeah, you have
You can add-
first of all, you have to have the cluster variables, right?
Sure, yeah.
Right. And so, you could add them into models. I mean, one thing you might do, if it's more of an exploratory thing, is you could get out estimates of the cluster effects from, say, a null model.
Yeah.
And then you could look at a correlation matrix of those with your cluster level variables, I suppose, something like that. Of course, it might be better to have a little bit more theory go on than that, but essentially, that's what you're trying to explain.
Because am I interpreting this right, that it could actually be a modifier, meaning that it helps us understand, like in that case, the pre and post test.
Right.
Does it tell us a little bit about for whom? Within that cluster, so certain classrooms
Yeah.
seem to have different, more variability.
Right.
Is
I mean,
there-
what I could do, that it might be, for example, here, so classroom curriculum, let's say, had a good, strong effect.
Yes.
It could vary depending on pretest level, though. I didn't explore that idea,
Yeah.
right? So I think what you're getting at now is there might be interaction terms or moderators. It might be that some classrooms did real well, others did not so well based on the intervention, and that could vary depending on other characteristics of the student or the
Students in
classroom.
the classroom,
Yeah.
Okay.
Don, can you, I'm sorry, there's somebody.
Yeah.
Yeah, suppose I want to build like a prediction model, multi-level prediction model.
Right.
There are statistics that can be used to measure how good this prediction model is, multi-level, without, because I know just the outcome might not be a good measure to understand how model prediction using this kind of data. Are there statistics that can be used to measure?
Yeah, I mean, these R-squares are sort of getting at that, and then there's been proposals for how to, so this is like an R-squared at each level. You might want an overall kind of R-squared, something like that. I mean, you could, another thing you could do is out of this model, you get the residuals, basically. If your model is really good, your residuals should all be pretty small. You could compare the residuals to the model with no predictors with the residuals that have predictors. So there's various proposals for things like that. Try to get an idea. Yeah.
So I just wanted to ask a sample size related question. So I'll ask the question more broadly, but I have specific examples in mind, of course. But suppose you're doing exactly this setup here, and you mentioned that there are some classrooms that have very few students. There are some schools that have only one or two classrooms. Most of when I learned about this stuff in the Pleistocene era, we were thinking about sort of this was something you did when you had a lot of data, and nowadays it's much more about having a reasonable amount of data at each level of interest. So can you comment a little on sort of when do you get into trouble here if you've got a single classroom in one school, for instance, but lots of schools have multiple classrooms?
Yeah, that's a good, excellent question, of course, and there's somewhat of a gray area. Andrew Gelman, he's like saying, do this all the time. Yeah. He doesn't care about the sample size. Other people have done simulations that have generally recommended if you want to include, say, classrooms as a level, you should have approximately 15 or more classrooms, something like that. These kind of rules of thumb. The danger, it's not really danger per se, but if you don't have many classrooms, let's say, you're not going to estimate the class of variance very precisely. Now, some people would say, who cares? I don't care if I estimate that very precisely or not. But the issue it also raises like singletons. Let's say you've got 20 classrooms, but several only have one observation. Those classrooms are not providing any discrimination between the within and the between variance. it's not like they're going to hurt you per se. But if you had a lot of them, it would be very difficult to estimate both the within variance and the between variance. One place that this comes up is more when you have, let's say you've got a dichotomous outcome. And this came up with my program Mixer. Somebody was using it and they couldn't estimate the model, and they're like, what's wrong with your program? And I said to them, well, how much did you pay for the program? It was freeware. You expect it to work too? No, what happened was they had an outcome. It was either alcohol or cocaine use or something like that. And they had like 4 time points. A dichotomous outcome, using or not. And what I found when I looked at their data set, like 80% of the subjects were either all zeros or all ones. So effectively, they did not have much longitudinal information in that case. That created computational problems because there wasn't a lot of information to differentiate the between and within variance. Now, that doesn't typically happen with the continuous outcome because there's typically some differences. But with a dichotomous outcome, you sometimes have to, so I put in Mixor as a diagnostic, how many level 2 units have constant dependent variable values? Because those, if there's a lot of those, then your ability to estimate these models is somewhat challenged. But I'd say otherwise, realize this, you have a classroom in with one student, it's not providing a lot of information for anything, basically. So having that in or out of the analysis is not going to make much of a difference because there's just not much information there. What that also means is you're not going to estimate that classroom effect as very well because you just don't have much information on that particular case. Yes, go ahead.
Related to
how important it is to estimate power?
Power? Oh, it's totally irrelevant.
So because
No, that's the right answer. Say that.
No, it's of course in designing these studies, and there's more and more software out there. Raudenbush has this program, I think it's called API Design or something like that. That's pretty popular for these. Much of the software that's out there for power is sort of like group randomized studies. If you have more complicated scenarios, then you have to call upon something like simulation to do it. And you can, I've done some of that myself in collaborative work is doing simulation. The thing that you got to think about is what are you powering for? Is it a level 1 covariate? Is it a level 2? How many units do you have? The other thing you need to have a guess about is the ICC. And the ICC can have a dramatic effect on power, actually. Even going from like, I mean, when I was first doing this kind of business, going from 2% to 5%, you think, oh, that's not too much of a difference. It can have a big effect on the power, actually. So, whatever kind of good pilot or baseline data you can have to guide the power analysis is very useful.
Well, we have something similar. I'm working on something similar to what you described with the drug usage.
Yeah.
And kind of decided to look at, take away the effect of longitudinal, so just come up with one variable used or not used. But there's still some other multi-level variables there, like family. So is that if it crashes with so much consistency among the time points, is that one way to handle it, or the other?
Yeah, so I mean, realize what I was describing is kind of an extreme situation where there was very little change across time. In most cases, there's going to be some change across time, and so, but realize if you do an aggregation across time, let's say, that, like across a year, were they using or not, let's say, that's fine, but what you're missing is what happened during that year. And you're missing, did they go up, did they go down, did they move around? So it depending on what you're trying to address, certainly you can do that, but you're kind of missing, it's like looking through a window and you're not seeing the entire landscape, basically.
Going back to the previous comment made about diving deeper into like the classroom level, and let's say there's a lot of variability between the classrooms, could you create more levels of that specific to say like a classroom with no teacher, a classroom with female teachers or male teachers, a classroom with...
I think that would be, I think of that more as a classroom covariance. like, is the classroom, is it taught by a male, female, something like that? I would consider those as not as a level, but as just classroom covariance. So they're trying to explain, this. Can I try to explain this by knowing certain characteristics of the different classrooms?
Yeah. So more demographics than the covariates.
Yeah, rather than a separate level. It sounds like they would be more like covariates at that level.
But even if it was more sophisticated, it could be in this classroom they taught it in the morning, in this classroom they taught it in the afternoon, in this class they had lunch early, whatever. It doesn't have to be. When you say demographics, it sounds like you're really limiting it. You don't have to. There's nothing limiting, but it does have to be a characteristic you can measure in each room. That's the real. That's the real.
See how that affects the outcome.
Right.
Sort of a related question. I get the idea of the null. You want to do a null model, and then you've got a full model. Can you, when you've got perhaps limited sample size and lots of variables, does that sound familiar? but
small and large P problem.
Yeah. So just some general strategies about how to tackle, some of the steps you might go through in the modeling. It's maybe clear when you've got an intervention that, of course, is your key variable. But do you have any other just, processes or guidance on the kind of steps that you would go through for a data set?
Yeah, and more of this. Right, in this is more like a clinical trial where the kind of design of the study dictates at least the outcome analysis. But in more exploratory or observational kinds of studies, again, I would say this is not any different than ordinary regression, really. So, what do you do in ordinary regression now? When you got a lot of covariates, you might do correlation matrices, things like this, to get an idea of what are potential candidate variables to consider. If you've got a real lot of variables, you might consider some kind of variable reduction techniques like factor analysis principal components before you throw everything into the model, I suppose.
Right. But like level 1 versus level 2, do you start with level 1?
Well, I think it depends on your interest, really. Here, it seems like there was a fair amount of interest in finding out at the cluster level what's explaining why students do better or not. So then I would be looking at classroom characteristics that I might have, and what's related to these student outcomes, basically. And again, if this was more exploratory, I might just get fit the null model, get the random cluster effects out of there, and then correlate those with other cluster variables to see what candidate variables might I consider.
So what's the biggest difference? I'm not expert in this, but what's the biggest difference between this and predictive modeling?
Well, the way of this particular one, this was more like a clinical trial in which I'm not necessarily trying to predict the outcome, but just establish whether there's an intervention effect or not. In predictive modeling, I think the big issue there is you can fit predictive models using classification trees or whatever, or really there's also work done on combining multi-level with classification trees. There's been some work in software on that. The issue there is always generalizability. You might come up with a very predictive model for a given data set. How well is it generalized? And then people do these kinds of validations. They do k-fold validation, things like that. So that's if you're interested in that within multi-level context, again, Sivanov he's got like a R program that has both random forest and multi-level. What they sort of do is they estimate one and then use the residuals from that to estimate the other, and then they kind of go back and forth. And then they also, I think, have within it the possibility of this like k-fold validation because, again, that's a critical issue in predictive modeling.
Can I ask one more? I think I'm perseverating on the same thing, but can you go back to the model that had, like the table that had the multiple? Because I really think that I've never thought about this.
Which one?
This is good here.
Okay.
So if you found something at the student level, let's say the television factor, right?
Okay.
but it's not, but once you took the clustering in effect, it's no longer significant. So that yes or no is not.
Right.
But does that give you an indication that there's some interaction within that cluster that's causing that to happen? That's what I'm trying to get an understanding. Is it just because the kids are somehow aggregated in this classroom, or is it possible that in that classroom, maybe in one set of classrooms, the TV got carried in and plugged in, and another one, I don't know, they put it on something else. Like, is there some way of knowing whether that change is due to a fidelity issue, especially when you're using it as a trial? Whereas in a drug trial, things don't change, but in interventions like we all do, there's so much variability that happens. That's not just at the who's in that cluster, but how maybe that intervention was even delivered.
Sure. Yeah, exactly. But the issue in drug trials too, they may not be taking the pills or whatever. But you're talking about fidelity, basically.
Something happening in that.
I don't think there's anything here that
tells you that
points directly to that. But you're certainly right that going beyond this, we might very well be interested in exploring. Okay, this says there's no television effect, and this says there was. Well, the reason I think that this changes is because the standard error here is quite a bit larger than the standard error there, because the independence assumption. But we might want to look at, it could very well be that the television was effective in some. So maybe I interact it with pretest. Maybe I find out some other covariates where it could be informative. I don't know.
So Elaine, just thinking about that, maybe there were eight different people who were delivering that intervention. You could look, I think, at an interaction term of the intervention by the person who delivered that intervention, right?
Yeah, you could potentially do something along those lines, or maybe you got some you gotta have some variable that indicates whether or not or how long they got the television, how many kids were in that classroom, things like that.
We collect those things, but this could be very useful because, for example, in a school classroom, we know kids cluster. They're in a classroom often because they all take the same schedule, so the kids may be more similar. But maybe something about those kids prefer television over not.
I think that's a cross-level interaction.
That's right.
You can have, let's say, age of children, and have that effect be then random and predicted potentially by something at level 2, like the intervention or something about the school.
Right, that's true. That's right.
But does this tell you to keep looking? That's what I was trying to get at.
I don't think necessarily.
I
think you're the one who tells you to keep looking. Yeah.
Interesting. Okay, well let's wrap up there, and please join me again in thanking everyone.